Okay, let's get started. Okay, hello everyone. Thank you very much for joining us today for the AIAA Los Angeles Las Vegas section webinar. Today I have two wonderful speakers, and they are the leader in their field. We have first one, Dr. Aki Roberge from NASA headquarters and Goddard Space Center. We'll before going into the introduction, we'll say a few things about AIAA. So first of all, if we welcome volunteers. So if you're interested in volunteer with us, please email our section chair, Dr. Sawani, with the email listed here, or you can contact me as well. So part of actually today's program is going to be recorded. If any question, let me know. So for the question for Dr. Roberge, please type in chat box instead of Q&A because it's easier for her on her end. Okay, so you can see our further events on aiaa-lalv.org/events. And you can also look at our membership information, aiaa.org/membership. And you can see on the top of the screen, we are offering 1 year free trial e-membership. You can look at it aiaa.org/emember. So today, this is the agenda at the bottom. In a few minutes, we'll be able to hear the wonderful presentation from Dr. Roberge. Okay, so a few words about AIAA. So we almost every Saturday we have great events arranged. For example, next week is Apollo 11 and Vikings anniversary. Actually, we have 2 more speakers. They are all veterans, in Apollo program or professor talking about the new lunar and Mars exploration. And this is our section chair, Dr. Chandrasekhar Sawani. He's a specialty engineer, and he is also a fellow of Royal Aeronautical and Royal Astronomical Society. He's associate fellow of AIAA and a fellow of American Chemical Society. He's the rocket scientist. There's just a few things. Again, for the first presentation, please type the question in chat room. If anything happened, disconnected, please keep trying. It should be resolved pretty quickly. Okay, a few words about Southern California. As you all well know, that Southern California has heavily aerospace populated. So, we have people like Northrop Grumman. They're building James Webb Space Telescope. That's actually related to today's topic. Is for exoplanets and astrophysics. That's expertise of Dr. Aki Roberge. And we also people building our defense, like EA-18G, the electronic warfare Growler, and the FA-18 Super Hornet, F-35, etc. We have JPL working a lot of things on, the Mars exploration, solar system exploration, and we have SpaceX, Virgin Galactic, USC, Aerospace Corporation. So why do you want to join the professional society? Because you are able to connect with other professionals, look at opportunities and more events and STEM outreach opportunities. So AIAA headquarters is Reston, Virginia. AIAA.org is the website. We are the local chapter based in El Segundo, California. So once you join AIAA, you can access the ARC, the journal, magazines, and Aerospace America Engage website. And a different level of education membership, we have a free 1 year free trial e-membership. Educator membership is also free. The student membership is pretty low cost. And this is some of the contact in our section. And today we're really honored to have Dr. Aki Roberge. She is really the expert in this field. She is planning to build the next, our future space telescope for exoplanets. So she's a research astrophysicist and in exoplanets and the astrophysics lab at NASA's Goddard Space Flight Center. She's currently on temporary detail to NASA headquarters. Her work focuses on the first one, planet-forming disks around nearby young stars, and the second, future space observation to observe, future space observatories to observe planets around the star, aka exoplanets. She received a Bachelor of Science degree in physics and planetary science minor from the famous MIT, and a PhD in astrophysics from also very top-ranked Johns Hopkins University. She's currently serving as a deputy program scientist for NASA's W1st mission in development, and was the study scientist for the Roberge mission concept study. In 2014, she received the Robert H. Carter Award for Science. She was a member of NASA's 2013 Visionary Astrophysics roadmap team, and is currently serving on the NASA Planetary Science Advisory Committee. So let's welcome Dr. Aki Roberge.
Thank you very much. Oh gosh, I sent this bio, I don't know, a month or two ago, and just in that amount of time, it became out of date. So first of all, as you'll see later on, the W1st mission has been given a better name. It's now the Nancy Grace Roman Space Telescope. And so that's life comes at you fast. All right, let me just see if I can share my slides. Do you need to stop sharing, Ken, or can I just go? Okay, you just did. Share screen. Let's see. I think, yes, that one. Okay. And PowerPoint. Okay. Let me bring up the chat. Okay, right. So I'm happy to be here with you today to talk about both a mix of science and technology is what I'm going for here. So one thing I like to do in my public talks that may be a little tricky here is that if you have a quick clarification question as we go along, I'd like people to tell me right away, because I don't want to find out at the end that somebody didn't understand some piece of jargon on my second slide and I don't find out for an hour. So quick little clarification questions, if you could type them in the chat window, I will try to pop over and take a look at it every now and then. But longer, more discussion type questions we should probably hold for the end. So okay, so I'll start with the amazing exoplanet discoveries that have been made over the last 25 years. So in case you hadn't heard, there are planets around other stars. And when I was in college, we didn't know they existed. So I'll very briefly go over where we've been and where we're going in this new field. If I can make my slides go. Oh, come on. Where's my mouse? Just a moment. There it is. Okay, there we go. Okay, so, and again, when I was in college, scientists thought that planets were probably very rare beasts. It seemed that the solar system, the theory had to be everything had to be so perfectly balanced for the theory to successfully form the solar system that we thought it was going to be a difficult thing to do. Turns out, the theory was wrong. Nature is kinder, and it's completely not the case. This movie that went by kind of fast shows a cartoon of all the exoplanets that were known as of several years ago, rendered as if they were all orbiting the same star. And as of a few days ago, when I checked the website, over 4,000 confirmed exoplanets have been discovered, and there are thousands more candidates beyond that. And these were mostly discovered using NASA's Kepler mission. And that's really only the tip of the iceberg, because from this and from other data, we think there's at least one planet for every star in the galaxy. So that comes out to over 100 billion planets in the Milky Way galaxy alone. That does not, however, mean every star has a planet, because a lot of these systems have multiple planets orbiting the same star, like the solar system does. Okay, but what was even more surprising, and pleasantly surprising, is that the exoplanets we've discovered are extremely varied. And there are types that we don't have in the solar system. So there are the huge, incredibly hot gas giant planets orbiting closer to their stars than Mercury orbits the sun. And those are the so-called hot Jupiters that were discovered first. There are warm, water-rich planets about the size of Neptune. Some people call them water worlds. They might be. There are rocky planets up to twice the size of Earth, which astronomers, typically and unimaginatively have named super-Earths. And we go all the way down to Earth-sized planets. Now, those Earth-sized planets might in fact be like the Earth with atmosphere and water ocean, but right now we just don't know. Despite what you see in the press about Earth-like planet discovered, we really don't know. All we know is Earth size. So this is the reason we don't know, is because when we detect exoplanets today, we're actually measuring the effect of the planet on its host star. So for example, NASA's Kepler mission, it stares at stars for years. It stared, I should say, at stars for years and measured their brightness. And some planetary systems are oriented edge on to our point of view so that one or more planets pass in front of the star from our vantage point. And this is called a transit. And when this happens, the light from the star dips by a tiny amount. And from that, we can calculate the size of the planet. But right now, in the vast majority of cases, all we can measure about exoplanets is their orbit, their size, and their mass. And in the best cases, if we're lucky, we can get all three. So basically, there's small black shadows to us right now. So we really want to go further and find out what their atmospheres are actually like. I mean, in the solar system, Earth, Venus, and Mars are, you know, kind of pretty, they're rocky planets, and given our precision, they're all about the same size. But they couldn't be more different from each other when you look at their surfaces and their atmospheres. So the first big step in this direction will come with the James Webb Space Telescope. And here it's in the clean room at Goddard in 2016. There's just this is just the telescope, and I believe the ISIM, the instrument science package, is on the back. I think it's integrated here. Okay, so the telescope and instrument package, they're currently at Northrop Grumman in Redondo Beach, where they were integrated with the spacecraft and the sun shield in last August. And actually, I got a chance to see it in their big clean room there with the telescope and everything attached to the sun shield. But I don't have any pictures of that because, of course, it was not allowed. So up until the COVID hit, the launch date for JWST was March of next year, but it has been confirmed that that date will slip. However, it will launch, and JWST will probe the atmospheres of many large gas-rich planets like Jupiter and Neptune, and ones that will tend to be warmer than Jupiter and Neptune in the solar system. And it'll tell us a lot about what they're made of, their atmospheres. Okay, so, but all of these discoveries, the vast richness of exoplanets out there, have led us to dream of a more ambitious goal, and that is to actually answer the centuries-old question, possibly millennia-old question, are there other truly Earth-like worlds out there? So we know that the Earth is unique in the solar system in that it has a moderate temperature, liquid water, a solid surface, and it has, most importantly, abundant surface life. In fact, it has a global biosphere that is so abundant and so robust that it is actually changing the bulk chemistry of the planet's atmosphere. And that is probably the only kind of life that we can actually expect to detect from interstellar distances. So to astronomers, the search for life is not exactly the search for life forms. It's the search for global biospheres. But this is still a question that fascinates scientists and the public alike. So for example, the 2017 discovery of 7 Earth-sized planets around a nearby star called TRAPPIST-1 created really an astonishing amount of public interest. The day of the announcement, there were, I got the stats for this from NASA, there were 2.5 billion non-unique users talking about TRAPPIST-1 on social media. And you know, NASA is very active in social media, but I'm pretty sure our public affairs people were taken by surprise by that. So yeah, and that's the up in the corner there is the Google Doodle from that day, which I think is really adorable. Okay, right, but to get to the goal of finding out if some of those small black shadows out there are actually really like the Earth, we'll need different observational techniques. The transit method isn't really going to do it. We actually need to see the planet itself and then analyze the light coming directly from it, what we would call direct observations. So the hard part about this is that planets are faint and they're located right next to bright stars. So it's like trying to see the airplane flying next to the sun. You can't do it until you put your hand up and block the bright sunlight. And that's basically what an instrument called a chronograph does in a much, much, much more extreme way. And this movie here shows the current state of the art. And for the first time in this talk, I am showing data, not artist conceptions. So this is a movie of 4 super Jupiters orbiting a large young star called HR 8799. And again, this is, let's see, it's a composite of images taken over several years with a chronograph on the Keck telescope in Hawaii. The bright central star would be in the center, but it's mostly been blocked out, except you can see some residual starlight, what we call speckles, moving around the edge of the chronograph mask. But the 4 dots that are clearly orbiting where the star, there they are. These are, like I said, they're 4 enormous gas giants, larger than Jupiter. They're super Jupiters, and they're orbiting very, very far from their host star. And this is another type of planet that we didn't know could exist. Okay, so why aren't we doing this right now for Earth-like planets around sun-like stars? So here is a brief description of the observational challenge. Okay, so in a nutshell, the Earth is ridiculously faint compared to the sun. It's 10 billion times fainter at optical wavelengths. And you know, it's difficult for pretty much anyone to wrap their head around what that means. So here's, people have used the analogy, it's like a firefly next to a spotlight if you're in DC and the spotlight's in California. That's actually too easy. That's actually not even hard enough. So I actually sat down and tried to calculate it more accurately, and I had an interesting time looking up the average brightness of glowing bugs. But this is what it comes out to. So if the sun, I put the sun at to the brightest artificial light in the world, which is the Luxor sky beam coming out of that hotel in Las Vegas. And if that's the sun, then the Earth is the brightness of 2 fireflies. However, that's, you know, astronomers have actually observed things that are about that faint already. The real problem is that faint source is right next to the bright star. So viewed from a distance of 10 parsecs, that's, astronomers don't use light years, we use parsecs, but it's about 33 light years, which really is not very far away. The maximum apparent separation between the Earth and the sun is 0.1 arc seconds. So that is about the width of a human hair viewed from a distance of 2 football fields. So the problem is trying to imagine seeing those 2 fireflies if they were basically sitting on top of the Luxor sky beam. So we need to suppress the bright light from the host star by a really extreme amount before we can see the faint Earth-like planet next to it. And no telescope and instrument that we have today can do that. So the question is, what are we going to do about it? How are we going to advance the needed tools? So the next big step in chronograph development will happen with the Nancy Grace Roman Space Telescope. And again, that's, as we talked about earlier, wait, let me just take a quick look at the chat for 1 sec. Is the data exhibited in a specific manner metadata? We'll have to come back to that because I don't understand the question. We'll come back to that at the end, I think. Okay, so you're right, Nancy Grace Roman Space Telescope, the next, NASA's next strategic astrophysics mission after James Webb. It's a 2.4 meter telescope that is much like the Hubble Space Telescope, but it is largely focused on studies of dark energy. However, Roman will also carry the first advanced chronograph into space as a technology demonstration exercise. There have been chronographs on space-based platforms before, but this one is the first one that will have active wavefront control. That in order to achieve much, hopefully, anyway, knock on wood, hopefully much, much greater contrast between, you know, star and the faintest thing you can see next to the star. So on the, I guess it's your right, I think. Yeah, on your right, there is a preliminary simulation of a multicolored direct imaging of a nearby planetary system. This is, you know, what we think we might see with the chronograph on Roman, if there was a warm Jupiter orbiting 2 AU from 2 AU, where 1 AU is the Earth-Sun distance, from a sun-like star that's at 3 parsecs. That's really very close, but still. So the planet is let me see if I can use my mouse here. Here's the planet. That's where the star would be. And this haze of light here on these 2 lobes on either side of the planet is not, in fact, unsuppressed starlight. It is light being scattered off interplanetary dust. It's a prediction for how the interplanetary dust in this system would arrange itself with in response to the gravity of this planet. And that dust comes from, it would be presumed to come from asteroids and comets within the host system, and it's very likely to happen. So again, Roman is being designed to push down to Jupiter and Neptune-sized planets orbiting in the warm inner regions of nearby sun-like stars. However, it is a technology demonstration exercise, so it's sort of best effort basis. But this whole endeavor, the Roman chronograph technology development effort, really is a very valuable technological stepping stone to the real prize, which is coming next. Okay. So Roman is really just at 2.4 meters. It's really just too small to study Earth-like planets around sun-like stars. They're just extremely faint. They're 30th magnitude in V band, and that is about 2 magnitudes fainter than the faintest sources in the Hubble Ultra Deep Field. So we need a much bigger light bucket and a much more ambitious space telescope that actually is designed for high contrast observations. So in January 2016, NASA began a concept study for such a space observatory. It's the Large Ultraviolet Optical Infrared Surveyor, or LUVOIR for short. Obviously, it's not a great name. It's a working title. And please, it's not French. Make sure don't say it LUVOIR, say it LUVOIR, like a pirate. It is a concept for a mission that is in the tradition of the Hubble Space Telescope, in the sense that it has very broad science capabilities. And again, as you might expect from the name, it is ambitious, and it will enable a revolutionary range of general astrophysics studies, all the things that Hubble addressed and more. After 3.5 years of study, we submitted our final report to headquarters and the National Academy of Sciences last August, and we presented to the Academy in November. And we should find out what the 2020 Astrophysics Decadal Survey thinks about the priority of building LUVOIR, and they estimate the spring of next year. That is maybe a little delayed because of COVID also. Anyway, so that was what you saw was the pretty movie showing the deployment. I think you can tell it has heritage. A lot of heritage with the James Webb Space Telescope. So, this is a 15-meter diameter telescope. Obviously, you have to fold it up if you're going to launch it. But here are a few technical highlights, which I thought this crowd might appreciate. So first of all, the LUVOIR architecture is scalable. And so we designed 2 variants of the observatory. LUVOIR B, on the right here, is large. It has an 8-meter diameter primary mirror. And for comparison, James Webb is 6.5 meters. Then there's LUVOIR A, which is really large. It's 15 meters in diameter. That's about twice the size of JWST. And it is, we think, given the expected heavy lift launch vehicles on the horizon, we think this is about the biggest telescope you will launch into space in one piece. Okay, to next little highlight. So both variants of LUVOIR will carry several different kinds of instruments at once. The candidate instruments we designed for the study are Eclipse, which is that advanced coronagraph I was talking about. LUMOS, which is an ultraviolet multi-object spectrograph. high definition imager, that's a wide field camera, a very nice one though. And then there's Pollux, which is a UV spectropolarimeter. And the design for this instrument was contributed by a European consortium with support from the French Space Agency, CNES. So, okay, so both LUVOIRs feature modular design to enable in-space servicing and upgrading of the instruments. We feel that the LUVOIR Science and Technology Definition team felt that the serviceability of Hubble was in fact a key scientific capability of the observatory, which is what has allowed it to remain at the cutting edge for 25 years, which is kind of staggering. But in addition to which, even if you do not in fact service LUVOIR, you probably still want modular design because it makes everything easier in integration and testing. If you can afford it. If you can afford modular design, you should have it. Okay, so in sum, LUVOIR, it's a powerful and hopefully feasible observatory to tell the story of life in the universe, from the Big Bang to hopefully global biosphere surrounding nearby, on planets surrounding nearby stars. And I just do want to say though, give a small shout out here to our industry partners on the LUVOIR study, Ball Aerospace, Harris Corporation, Lockheed Martin, Northrop Grumman. And they helped us all along throughout the study. And we are in fact relying on them to really mature and develop the technologies that we need for this mission. And I believe, and that work is still going on, even though the study is officially ended right now. Okay, so now let's pretend it's 2040 and LUVOIR launched and checkout is done and maybe the first year of operations is over. This is what we want to see with LUVOIR, an image of a planetary system that looks like our solar system. And this is a simulation of the inner solar system in visible light, viewed from a distance of 13 parsecs, that's a little further away, with the coronagraph on LUVOIR A. So Jupiter is just booming bright, it would probably saturate actually. And Venus is visible right here, just outside the inner edge of the coronagraph. And, well, the coronagraph suppression region, I should say. And here is the pale blue dot that we're looking for. So a couple of things about this you might notice. Why does Venus look green? You know, isn't Venus more yellow? Well, that's because the inner working angle, the region within which, the region exterior to which you can see things with the coronagraph, the part that isn't blocked. The size of the inner working angle is, it depends on wavelength. It goes as some factor times lambda over the diameter of the telescope. So that means that basically the inner working angle of the coronagraph is larger in the red, and Venus is sitting right at the edge of the inner working angle. So the blue light comes through, the green light comes through, but the red light is being blocked. So that distorts the color for Venus. So, however, if you know about it, you can correct for it afterwards. But more importantly, you know, Earth is, you know, Earth's right out here, nice and clean, decently outside the inner working angle. So, but pictures of planets, as attractive as they are, this is not the real goal for LUVOIR. We want to actually measure the planet's atmosphere and the surface conditions using light reflected from the planet. And then further, we want to analyze that light and see if there are signs that the planet has life on it. And in designing this experiment, the Earth really is our model, because it is the only global biosphere that we know of. For example, while we may think that the subsurface oceans of the icy moons of the outer solar system, like Europa, may have conditions that would allow life at the bottom of the ocean, but we can't even tell if Europa is inhabited right now from the outside, and it's right next door. So really, you know, Earth with its global biosphere, its exposed surface, its its atmosphere that has a completely different chemistry than it should have if it didn't have life. That really is the model that guides all of our thinking and the design of, not the design of the scientific experiment, and then the hardware that we have to build in order to execute it. All right, so let's consider Earth's atmosphere. Right, so this plot shows the visible and near infrared light reflected from the Earth as if in 1 pixel, the disk integrated spectrum. And so the bottom of the plot is faint, it goes faint at the bottom, bright at the top, blue over here, red over there. So 0.4 microns to about 2.4 microns. And it's the light spread out by wavelength. And this slope here, this rise in brightness on the far left, that is literally our blue sky. That's the Rayleigh scattering right there. Okay, so next feature. Why am I not? There we go. Okay, so this shallow, sharp, well, it's not that shallow actually, this sharp dip right here, this nice clean feature, that's caused by molecular oxygen. And so that is the waste product of photosynthetic life that we are breathing at the moment. And over here, all of these broad and deep dips, this one, this one, this one, this one, these are all water vapor absorption features, and they point, their strength and depth point to the fact that there is liquid water on the surface of the planet. And then finally, over here is part of a methane feature. So in our atmosphere, methane is largely produced by bacteria that live in the guts of our livestock and in swamps. And interestingly, oxygen and methane could not be present in our atmosphere at the observed concentrations without life. They are what some people call in disequilibrium, and that making them biosignature gases. Although most astrobiologists disfavor the simple, these days anyway, disfavor the simple saying that we're going to look for disequilibrium chemistry on exoplanets. Because that is quite a gross oversimplification, because any molecule or even pair of molecules can or cannot be a biosignature in a particular context. There can be molecules that are in disequilibrium even though they don't arise from life. So another way of looking at it, the way I try to look at it without like hurting my brain, is we'll get data like this, as well as a whole lot of additional information about the planet and its host star, as much information about the whole system as we can. We will try to explain what we see with detailed physics, chemistry, geophysics, make it as detailed as we possibly can. And if we still can't explain what we see, we will turn to the other science left in the building, and that's biology. So in a way, the experiment is we will succeed by failing to explain the data. Okay. So also, LUVOIR would have a supporting role to play in the search for life nearby within the solar system. I mentioned Europa earlier, and the discovery that many of the icy moons of the outer solar system have subsurface oceans really dramatically expanded scientists' thinking about potentially habitable environments. So these subsurface oceans must be heated from below, probably by geothermal activity. And geothermal vents at the bottom of Earth's oceans harbor life forms that do not depend on sunlight for energy. So most scientists think that Europa and the other ocean moons of the outer solar system are the best chance to find life in our backyard. So this image shows ultraviolet auroral emission coming from Jupiter's moon Europa that was observed with the Hubble Space Telescope. And this is Lyman alpha, hydrogen Lyman alpha emission coming from the breakup of water vapor in plumes that are emanating from the surface. And those plumes, hopefully, can provide a glimpse into the deep oceans. Okay, so and these are simulations of how Lyman alpha emission from Europa might look to LUVOIR. Now these are based on a model, so who knows if they're right. But still, it would have the LUVOIR would have the sensitivity and the resolution and the right wavelength coverage to monitor Europa with flexible cadence over long time scales. determine the time dependence of this activity, and do this for other, for other icy moons as well in the outer solar system. There's actually a quite impressive amount of solar system remote sensing that could be done with LUVOIR, because the 15-meter LUVOIR has a spatial resolution in the optical that isn't that different from the spatial resolution of the imaging camera on the Juno mission, which is actually orbiting Jupiter. Of course, LUVOIR can only detect photons, and solar system spacecraft absolutely detect more than photons. But it would provide high resolution and flexible cadence, and best of all, you can point it anywhere in the solar system exterior to the orbit of Venus. Okay, right, so you can learn a ton more about the LUVOIR mission concept on our website. Full range of science goals. I didn't even touch on in all of our astrophysics science goals. There's more technical detail, the team members, and there's some links to popular articles as well. And if you have the stomach for it, you may download our final report. The final report part is over 400 pages, and the appendices are also over 400 pages. So if you have the stomach for it, you can take a look, you can go there. But I will point out that the first chapter of the final report is intended to be a much shorter, more digestible, but complete summary of the entire 800 pages. So, okay, and sort of head towards the wrap up here, I want to emphasize that finding out if an exoplanet is inhabited will call on a wide range of expertise, from biology to geophysics to astronomy, technology, stellar physics, all sorts of things. So the search for life really isn't the domain of one scientific discipline alone. It draws in all parts of NASA and more. And here's just a sampling, just looking at the NASA parts. So understanding the impacts of the sun on solar system planets via space weather is really key for understanding what kinds of stars can be hospitable for life. Obviously, life can arise on a planet around a sun-like star, but a lot of the Earth-sized planets we have discovered so far are actually orbiting the much more common red dwarf stars. These are lower mass than the sun, and they are far more active. They're much, much more active than the sun. And so understanding whether planets around those kinds of stars can be Earth-like is really probably the next important question that people will be tackling in the next decade. Again, as I hope I explained, Earth itself is our best and only template for a habitable and inhabited exoplanet that we can actually study. And it's the model that guides all of our endeavors. And then Mars was once warm and wet, and actually ditto Venus too. Venus and Mars were both far more habitable than they are, we think anyway, they were far more habitable than they are today. And so they really are very important test cases for understanding the boundaries of the stellar habitable zone, and maybe even more importantly, the evolution, the time evolution of habitable conditions. And then again, like I said, the ice-covered ocean moons of the outer solar system's moons like Europa and Enceladus are the most promising places to look for life in the solar system right now. And then finally, let's play the little movie again. Everything we learn from all of these studies guides the search for Earth 2.0 and the life among the stars. Okay, and so to conclude with the NASA exoplanet mission swoosh, exoplanet studies began with ground-based telescopes, which are still playing a major role today. Then new kinds of observations were enabled by Hubble, Spitzer, and Kepler, these missions here. And of these three missions, only Kepler was actually designed to study exoplanets. The TESS mission, which is currently up right now, it uses a technique that's basically very similar, basically the same as the technique that Kepler uses. It will continue to search for exoplanets around nearby stars, and just, but again, we're talking about discovery of small black shadows. So we're sort of filling out the address book for the solar neighborhood here with TESS. Then JWST will be the big leap forward towards from just discovering and counting exoplanets to trying to characterize them as individuals by probing their atmospheres. And then after that, there's a path, possible path stretching out over the next decades that leads through the Roman Space Telescope and its coronagraph technology development program to ambitious missions that could actually execute the first surveys for truly Earth-like planets out there and seeing if some of them actually have life. And furthermore, and so I should mention, I focused on LUVOIR, of course, because that was the one I worked on for 4 years. But another variant of another kind of exo-Earth mission this is called Habitable Exoplanet Observatory, was also studied at the same time and over the same duration. HabEx has similar science goals to LUVOIR, but a 4 meter telescope. It's smaller, but it does feature, in order to partly make up for that smaller collecting area, it uses a free-flying star shade to help with its starlight suppression. That's a whole nother talk if you want to hear about star shades. So anyway, but with these missions, LUVOIR, HabEx, these days I just sort of smush them together and I call it LUVEX, because they really all are observatories in a family. And this LUVEX, I'm going to call it, if Earth-like life in global biospheres is not extremely rare, then we will have a fighting chance of finding some. And so we're really in the exciting position of possibly answering an ages-old question about our uniqueness in the universe, or finding out if we're even asking the right questions. Okay, so that's all my slides. And there looks like there's heaps of time for questions, because usually when I give a talk, I'm stopping as people ask questions as they go along. But that's a difficult way to do things, obviously, when we're doing it when we're doing it remote. So I think what we can do now is turn to questions. And let me take a look at the. Okay, let me figure out if I can take a look at the chat window. There we go. Find my mouse. Okay. All right. Let's see. Yeah. Okay. I guess I don't know how you want to do this. Ken, do you want to unmute individuals? Should I call on people? I guess the first question looks like it's from Lisa Gethard.
Okay. I'll unmute her.
Okay. Okay. I guess Lisa, you need to unmute yourself as well. It looks like. There you go.
Hi,
Lisa?
can you hear me?
Yes.
Hi, Dr. Roberge. Thank you so much. This is a wonderful presentation. And I am so interested in, like you mentioned, the Roman telescope, W-FIRST. There are things, I'm very involved with a lot of technology and the science portion. How can we help? I'm a solar system ambassador and a ISS space station ambassador and involved with STEAM for our students. To keep them occupied, there are different things I'm trying to keep them interested in with coding, like there's Jupyter, Python coding, there's data. What can we do to provide services for your endeavors with your research continuing so that it's not lost, but the 21st century workforce of our students keeps going forward with interests like this?
Oh, okay. Well, that's a large question with a lot of potential answers. Let me just start with what popped into my head. Okay. So, okay, first of all, there are things that students and the general public can do right now to actually help advance exoplanet science, exoplanet research, original research. We call this citizen science. And Kepler was really good with this. It's called Planet Hunters. And it was interesting because it found that they have a whole system set up for this. It works very well. And it was interesting because we found, or they found, that human beings could find some kinds of planets that the pipeline, the automated pipeline, really struggled with. So like multiple planet systems in binary systems that had multiple planets and multiple stars, like, you know, Tatooine style if there's a binary star. So they did a lot of that with Kepler. That is, I believe, that I'm pretty sure, 99% sure that is still going on with tests, using test data.
Yeah.
So that's sort of the astronomy. That's one way that could, you know, that people can help advance exoplanet research right now. On the technological sides, on the more technology sides, that one I'm much far less sure of the answer of. I think if you wanted to get some thoughts on that, I mean, maybe the question could be directed to some of our industry partners, or you might want to ask for a talk from the lead engineer for LUVOIR. I describe engineering. I don't necessarily
No,
do it or understand it. I just describe it.
I completely understand.
Yeah.
In our state of South Carolina, our Department of Commerce, we have a program that allows any resident of the state of South Carolina to learn how to code for free.
Good.
So we have platforms, yes. So we have platforms available that through our library systems, through our students, our workforce, you know, from home, they can learn how to code in HTML, C, C++. But I understand that through NOAA and NASA JPL with some of their programs, they prefer Jupyter Python.
Yeah, well, I'm old school. I use IDL, and my students mock me for not knowing Python, but I think probably probably got to learn it someday here. Yeah, all of those things are useful because, like, certainly, like some of the more major heavy duty codes aren't going to be done in Python. They'll be done in C or something like that.
Okay.
So it does make me think, though, that is excellent background to prepare students to apply for the NASA summer internship program. You know, that's NASA wide, and it can happen remotely for a lot of things. You know, there are some things that can't be done remotely. Some of the internships that would have been like hands-on in the lab, obviously that's not happening now. But a lot of stuff is. So if you Google NASA undergraduate internship program, you'll find it. But actually, I should say it's not only for undergrads too. It's available to graduate students too as well.
Yes,
So,
I have that.
yeah,
Thank you so much.
Sure.
It's been wonderful. Thank you.
Great. Let's see. I think the next one is, let's see. Okay, actually, the next question was also from Lisa. So, but maybe we should give somebody else a chance first here. Let me just try to scroll down.
I think next one is either Tom or Victor.
Okay. I don't see Thomas here. I guess the Victor. Okay.
Yeah. Yes. Can you hear me?
Okay. Yes.
Okay. I was wondering, of the you have the space-based observation system, space-based observation systems opposed to ground-based observation systems. Which orbit? How far out of the telescopes we have? Which orbit do we have those in? As for the space-based observations, that in the outer planets out there?
Okay, that's a great question. So let me answer the first part of this that as relates to telescopes, like which is what I do. So I'm talking about space-based telescopes as opposed to like solar system spacecraft.
Yes.
Yeah. So Hubble is in low Earth orbit. It's whipping around the planet every 90 minutes, and it's a little unstable.
That's far enough.
Yeah, it's not that far up. I mean, it had to be reached by the space shuttle, right? So, but still, it's in space. So we don't have to look through the atmosphere. I mean, trying to do ground-based astronomers will be irritated with me for this, but I actually think trying to do astronomy from the ground is it's really, it's hard. I mean, it's like you're looking from you're at the bottom of a pool and you're trying to look at something outside. So just being in space provides enormous advantages. Also, it opens the wavelength range you can look at, because you cannot do ultraviolet from the ground. You can have ultraviolet astronomy from the ground, or you can have ultraviolet astronomers on the ground, but you can't have both. Without our ozone layer, we wouldn't have life. Humans would be dead. So Spitzer was in a drift-away orbit, I think. No, yes, I think it was. Kepler was in a drift-away orbit. TESS, TESS is in a really weird orbit, actually, a really weird halo orbit.
These are much higher than the Hubble?
Yeah,
or
higher. Yes, higher. Because none of Spitzer, Kepler, and TESS are not intended to be serviced.
So some are beyond outer orbit.
And then James Webb will be at the Earth-Sun Lagrange 2 point, or Sun-Earth Lagrange 2 point. That's the prime real estate where every new telescope wants to be. So James Webb will be at Earth-Sun L2. Roman will be also, and ditto also LUVOIR and HABEX. It's really a nice place to be. It's the prime real estate for a telescope.
So of the outer planets, has there been any study to position telescopes on some of those outer planets for better view? Or is that just kind of astronomically impossible?
No, first of all, it's impossible. Second of, well, at the moment anyway. Second of all, I don't think it gives you any advantage. No, I mean, being on a surface without having any infrastructure there, like, roads, cars, gas tanks, liquid nitrogen tanks and things, there's no advantage to being on a surface without the infrastructure. This is what the advantage the ground-based observatories have compared to space-based observatories. They can fix them. They can fix them easily, upgrade and fix them. And that was one of in Hubble was upgradable and fixable, arguably not easily. But without the infrastructure, there's no advantage to being on a surface.
So these are the ones that have spotted the exoplanets solar system. Is that correct?
Yeah. So all of these missions and those ground-based observatories have all either have or will all study exoplanets in some fashion. But they also have other goals as well. They have other science goals as well.
So they're not that far away then. The exoplanets are not that far away.
Relatively speaking, yeah.
Okay, so
like for example, we know there is an exoplanet orbiting the star that is closest to the sun. There is an exoplanet around Proxima Centauri, and that's only about a parsec. That's only about 1 parsec away.
Yes, that's what the second push-up connection.
Yeah. So no, they're planets. They are so exoplanets. They're just so common that these are not that far away by astronomical standards. Of course, they are ridiculously far away by any sort of human standard.
I understand. So have you been able to determine how far away, in relation to the Sun-Earth astronomical unit, how far away have you spotted an exoplanet system where you've actually spotted an exoplanet and its sun approximately the same distance as the sun is from the Earth? On that system.
A planet's at about 1 astronomical. Yes. We've discovered planetary exoplanet systems that have a planet that Earth's about 1 AU from its star. The Earth-Sun distance. Most of those are big though. They're those warm Neptunes I was talking about. Just because we just aren't sensitive enough yet for truly Earth-sized planets around sun-like stars. We have also discovered small Earth-sized planets that are orbiting these low-mass, cool red dwarf stars. So they're orbiting. They're in what we call the habitable zone. So they're orbiting closer to their star, but a planet at that distance would be about the same temperature as the Earth if it had an atmosphere like the Earth's. So, because the star, it's sort of like this. The habitable zone is like, okay, so here's a sun-like star, and right about where the Earth is and a little extending further out, that's a good temperature. That's like the the Goldilocks zone, where you're about the right temperature to have liquid water on the surface if you have an atmosphere.
Right.
Then for the smaller, the low mass stars, they're cooler. And so the habitable zone sort of huddles in towards this campfire to keep the planet warm, so that the planet would be warm. And then for the brighter stars, the habitable zone backs off so that the planet doesn't get too hot. So the planet would need to be further away, or else it would be too hot. So that kind of answers your question. I think it answers the intent of your question anyway.
Yes, thank you.
So, okay, cool. Oh yeah, so let's see, I guess it was, let's see, I see Victor, then I see, next in the list, actually I see Erin, I think.
Yes, can you hear me?
Okay. Yeah, sorry, who is this again?
Well, this is, I forgot that my Zoom has my wife's name.
Oh, okay.
My name is Jacob, actually.
Oh, okay, that's fine. It just surprised me is all.
Yeah, I didn't notice that until right when you mentioned it.
Yeah.
I guess my question
Okay.
is a little bit of a follow-on to the last one, was that because all these telescopes, we would like to place them at the L2 point. Earlier, you mentioned serviceability. So can you expand on that a little bit? Is that part of the report, any investigation into that type of thing?
Yeah, see, what we've done, our mandate was to deal with the LUVOIR side of it. So we designed with serviceability in mind. So let's see, what was it again? So the prime, quote, prime mission lifetime is 5 years, like it is for every telescope. Then we have 10 years, we planned for 10 years of onboard consumables and a 25-year lifetime goal for non-serviceable components like the mirror, like the primary mirror. And then, like I said, it was, we designed with modularity in mind. We also went to the satellite, they changed their name, I think. They were called the Satellite Servicing Office at Goddard. I think they've changed their name, but I don't remember what it is. But they gave us, at the beginning of the study, they gave us sort of a handbook, a sort of like, serviceable design for dummies. And it was like, use these latches, these valves, this, that, and the other to try and make things standardized and hopefully enable robotic servicing and whether you actually, I'm completely agnostic. I do not care whether it's robots, humans, or some combination of both, which is probably even more likely. I expect probably you would not do, I don't know. We dealt with the LUVOIR side. The other half, like the servicing infrastructure of how you were, all the rest of that stuff, that was outside of our purview. And
Sure.
It's also outside of scope for NASA's Science Directorate. We couldn't. But the ideas that were out there, I think what was said is that it makes most sense energetically and probably also in terms of infrastructure and just how workforce. If you bring LUVOIR back from L2 and bring it into like maybe like a high lunar orbit or a high Earth orbit or a lunar orbit, and then do your servicing from there.
Oh wow, that's interesting.
Yeah, and then send it back, because a robot that you sent all the way to L2 would have to be 100% autonomous. Whereas if you're doing this somewhere near, say, for example, the Lunar Gateway, then you could have teleoperations, telerobotics with humans in the loop. That's probably a better idea. And the energy to do that, to go from L2 to like a gateway orbit, is minimal. It's totally worth the cost. So.
Okay. So the serviceability idea might be something like a spacecraft goes out there, docks with it, and
docks it to
pulls
bring it back.
Okay.
Like a tugboat, I think. But may I say, everything I'm saying here is just basically this is total speculation, because we will design the observatory in response to the servicing infrastructure that exists, not the other way around.
Sure, makes sense.
Yeah.
Okay, thank you. That's very interesting. Thank you.
Yeah. Okay, so let's see. Thomas, I guess, is next.
Yeah, Thomas
Yes.
is okay.
Would the LUVOIR be able to see a planet in the entire habitable zone of a red dwarf like Bernard star, do you think?
Yes, surprisingly enough, we can. Now, I'll point out that LUVOIR we designed it for the key goal of looking for Earth-like planets around sun-like stars. However, it's such a powerful observatory that we can do those kinds of planets around a good number of the small low mass stars as well, the red dwarf stars. I don't know if Barnard's star was specifically in the list or not, but we do have a list of nearby red dwarfs that LUVOIR could actually take a direct image of, take a picture of a habitable zone planet around that star. Yeah.
As
so basically,
as you go the other way, how does the telescope, if you're in like an A-class star,
yeah,
are we getting to a point that it goes?
We can. You raise an interesting point, actually. That I wish I had a slide from a different talk. But there's sort of a sweet spot in the type of star. So, and it has to do with how the habitable zone changes in size with the temperature, the brightness of the star. So with those small, dim red dwarf stars, the habitable zone comes close in. That's bad for direct imaging, and you have to push your coronagraph to smaller inner working angles. But the contrast ratio between the planet and the star is more favorable. Then if you go to the high mass stars, like the F and A stars, the habitable zone moves out. That's good. You're well outside the inner working angle. But the star is much brighter, and the planet to star ratio goes down. So the planet, it's really, it's like two different things you want to make the thing detectable. You want it to be far from the star, and you want it to be relatively bright compared to the star. And these two things go in opposite directions on the low mass star end and the high mass star end. And, in some ways, LUVOIR is in this relatively, actually the sweet spot is actually probably the K stars, to be completely honest with you, not G stars, but LUVOIR is in this like F, G, K, M. So, but we're focused on the FGKs.
Okay, all right. Of course, the smaller, hopefully the longer lived star, and maybe the potential for life to have developed.
Yeah. Yes.
Longer term.
That's the other thing for those who don't know. The high mass stars have short lives, and low mass stars have long ones. And I think there are a few people out there who think you can have habitable planets and life in the habitable zones of A-type stars, but I would have to put them in the very, very distinct minority. Like I can only think of like 2 people. So A stars are probably not. I actually study A stars a lot for planet formation studies, because in that case they're actually easier to study, not harder. But probably the sweet spot, we'll do FGK. Those look like the best, and probably K stars are the real observational sweet spot. Just a little bit lower mass than the sun.
All right, thank you.
Yeah. Okay, what do we got here? Let's see. Comments. Aaron John next to enemy. Raise your hand. Okay, that looks. Unless Errol has or has not spoken, that looks like all the questions. Maybe. I'm not sure. I don't know who Errol is. I didn't see a question.
Yeah, Errol is actually AIAA member in Orange County.
Okay. So, hi.
Okay, when you're traveling to a far domain where you don't know too much, you're not familiar too much, how do you assess the loads when you're designing the equipment, things, measuring units? What is the procedure, roughly, in other words? How do you define the loads? To design something, you need loads.
I'm sorry, did you say laws?
Loads. Load.
Loads. L-O-A-D-S. Loads.
L-O-A-D-S, okay.
Okay, so you want to know how you're asking about our launch vehicle and
if there was a mission there before, probably there were measurements taken before, but when there is a new adventure, you don't know nothing about it yet. So how do you define the loads? Estimate?
Loads. Are you talking? Okay, let me see if I can understand the question. Are you talking about the launch loads?
Launch loads are known. I worked in Delta IV myself, so they are known. But when the satellite goes out in the deep space, now it is an unknown domain, basically.
Well, I mean,
according to the trajectory and according to the closeness to the sun, probably some estimates can be done.
Okay, well, all right. I think I see what you're getting at. Now, first of all, I guess I should point out that the Earth-Sun Lagrange 2-point is not that far away from the Earth. You know, it's a high orbit for a space telescope, but compared to solar system spacecraft, it's nowhere we haven't been before. It's pretty close by. And I thought you were asking about launch vehicle options, which is why I had this slide in backup.
Yeah, that is easier. There's no this one.
Yeah. Well, I mean, it isn't.
High, you know.
Yeah, it is. I mean, I do want to say, you know, nothing. You know, launching a telescope of this size is not easy. If you look at these lists of potential launch vehicles on the left, you'll notice that none of them actually exist yet. But the fact that there are multiple options, maybe hopefully on the horizon, is very encouraging. And LUVOIR B fits in all of them with margin to spare. These percentages are showing the percent margin. So look at this one here, the SpaceX Starship, 86% margin. We could almost launch 2 of them. This is mass margin. Obviously, volume margin is more constrained, and that's what's really limiting us. And that's why, so these are showing LUVOIR A, no, sorry, this is LUVOIR B packed into SLS Block 1B, and that's LUVOIR A packed into SLS Block 2. That's LUVOIR A packed into Starship, their current fairing, and that's LUVOIR B packed into the Starship. LUVOIR A is a very, very tight fit, but LUVOIR B is got room to spare, and there's plenty of mass margin. LUVOIR A is tighter. We have New Glenn won't do it, and SLS Block 1 won't do it, but there are some other options for LUVOIR A. Anyway, that's what I thought you were asking, but no, I mean, as far as environment goes, Earth Sun L2 isn't that far away. It's nothing too weird, and it's just deep space. You know, it's deep space. It's not like you're even in orbit of a solar system planet where you have to worry about magnetosphere or anything like that. It's nice, calm, quiet. That's why telescopes want to be there.
Okay, thanks.
Sure. Okay, and briefly describe the differences between LUVOIR A and LUVOIR B again. There were some, well, the big one, the obvious one was size, and that is what I talked about. However, it's more than size if you're looking at this one closely. Let me see, play please, there we go. Okay, so yeah. So the next big feature, there is a real significant difference between these, but you know, aside from their size, their simple, you know, straight up collecting area. LUVOIR A has the secondary mirror is on axis. The secondary mirror is right here, so it obscures the telescope, the hole in the telescope. Having a hole in the center of your telescope, as a rule, is not great for coronography, for using a coronagraph. So we worked really hard to make this hole as small as possible. The secondary is as small as possible, and this hole here is as small as possible. It's proportionately much smaller than the hole in the JWST mirror. And that was to improve the performance of the coronagraph. But coronagraph would prefer, even better, don't have an asymmetry in the center of your don't have an asymmetry in your telescope at all. So don't have a hole in the middle. And so LUVOIR B was designed as an off-axis. So this right here there's the secondary mirror, and it doesn't obscure the primary. This is a lot like JW, and everybody's pretty comfortable with this. This is, you know, technologically, I don't know, it seems fine, but some people seem kind of jittery about it. But it makes the coronagraph perform better, which partially makes up for the fact that this telescope is smaller than LUVOIR A. So that's the really, from my point of view, the two key differences between LUVOIR A and B. One, size. Two, on-axis versus off-axis. Other than that, they're extremely similar. Other than that, they're extremely similar.
Okay, thank you. And is LUVOIR B, is that considered a a design evolution from A, or are they both still active alternative concepts depending on scope and funding and all that?
It kind of, yeah, well, it's sort of both. Yes and no. I would say we designed LUVOIR A first. And then we realized that if we just replicated this kind of design for 8 meters, it wouldn't perform, it wouldn't give us the numbers of exo-Earth candidates that we really wanted. So we went to this off-axis design to get the yield, the science yield back up. So you could, in that sense, it is an evolution of the LUVOIR A design. However, that doesn't mean that this is just categorically better. It depends on the size of the telescope. If your telescope is much bigger than 8 meters, you probably will want to go on axis again, just because it doesn't pack well into a launch vehicle.
The off axis does not pack
well? Yeah, it's because the secondary mirror strut has to be longer in this case than it is. The distance from the primary to the secondary for LUVOIR B is longer than it is for LUVOIR A.
Okay, all right, thank you.
Yeah, actually, if you want a ton of detail about why that is, I have that in a different presentation. I basically understand it, but perhaps a talk from our lead engineer would actually be the right person to explain it.
Okay, yeah, thank you. I'm an engineer, so that's why my questions go in this direction.
Well, if you go to that website that I pointed out, there is a longer version. These little snippet movies that I showed here with the engineering highlights, the design highlights, are snippets of a longer movie that's available on our website. And I think it does address this issue about the secondary mirror.
Okay, thank you.
Sure. So where was that? This website. There you go. This one. So. Okay, so let's see. Is that all? I guess, what time?
Yeah, it's, we have like 2 minutes.
Okay.
Yeah, so well, there is one more. Okay, Arrow, you can speak out. Arrow.
Hi. You just closed the screen. Are these light blue telescopes or concentrators possibly? Are they inflatable ones?
Light blue telescopes. Which ones?
You just closed it. You just closed the picture. There were 2 of them. One of them is 15-meter diameter.
Yeah. Okay.
The next one, the next page.
Inflatable? I don't think.
Yes,
do you mean,
yes. Okay, this one.
Yeah. Do you mean
the one on the left is 15-meter? The one on the right is 8-meter. They are huge, basically.
Yes, they are huge.
Are
do you mean
inflatable members?
I'm assuming you don't mean inflatable, but you mean deployable. They fold. They fold up.
It's obviously deployable. Something deployable.
Yeah.
But
this here. What?
Inflatable. This is what I'm talking about.
I guess I'm not
How
sure.
the deployment is done by
Right here.
inflation?
No.
Inflating?
No.
Okay.
This is the deployment right here.
Okay. Thank you.
Yeah. If it folds, it's a heritage based upon the James Webb Space Telescope.
Okay. Thank you.
So it's folded basically.
So it's some kind of mechanical.
Yeah.
Awesome. Okay. Thank you.
Yeah. Yep. There's the key part right there. So it's much like James Webb, although this part is different. The articulating arm is a new feature for LUVOIR. It's actually JW can't do that. Cannot articulate the telescope separately from the sunshade. But this is actually, that's a nice improvement actually in the LUVOIR design. Okay, I think that's, I guess that's all the time, right, Ken?
Yeah.
Okay.
That's right. Thank you. Yeah, this is fantastic. As you know, this space telescope, exoplanet means the future of the space program, and a lot of, great opportunities for all generations, but of course for younger ones, and they can, learn, those engineering science, and to prepare for themselves for the exciting program in the future. They keep learning from Dr. Roberge, and that's really fantastic. So we'll keep in touch with Dr. Roberge, for a future presentation or a workshop. and really appreciate. Yeah, thank you so much, Dr. Roberge.
Okay,
Thank
you're
you.
welcome.
Thank you.
Thank you.
Great questions.
Yeah.
All right, let me get off here. Stop share. There. Okay.
All right. Thank you. Thank you. So let's see. Our next speaker is Mr. John Thornton. John, are you here?
I am here. Unfortunately,
Yes,
I had to call in.
Yeah, I figured out that's your number. Okay, so let me put up the introduction. So that's okay. So John Thornton is CEO of Astrobotic Technology Incorporated. He is the CEO, Chief Executive Officer of Astrobotic, which is located in Pittsburgh, Pennsylvania. That is a space robotics company, and where he's responsible for leading the company's mission for making space accessible to the world. He leads by attracting technology contracts, equity investment, and the payload customers. He also oversees the team for the company's product line for lenders, including Peregrine. If I spell, let me know, which is set for the mission for 2021. Prior to Astrobotic at Carnegie Mellon University, Thornton led the build of ScarRab, a NASA concept robot for lunar polar exploration. It was the first robot to carry a prototype of NASA's Resolve payload. He also founded Carnegie Mellon's Advanced Composite Lab and R&D and the manufacturing lab specializing in high-performance lightweight composites for robotics. He holds a master's in mechanical engineering and a Bachelor in Science in Mechanical Engineering from Carnegie Mellon University. So let's welcome John for his great talk today. So, John, I'm going to put
thanks so much for having me here today. I guess I'll be asking to work through the slides remotely, and hopefully we can make that work.
Okay, I'm posting the slide now.
Awesome.
Okay, let's see.
So yeah, my name is John Thornton. I'm the CEO of Astrobotic, and Astrobotic is a space robotics company. We're building a delivery service to take payloads up to the surface of the moon, and also a delivery service to take payloads across the surface of the moon. So today I'm just going to talk a little bit about how we think about space, why we do it, and then I'll go into our Peregrine lander and our missions and what's going on there, and show you the latest updates on progress on our missions. And then after that, we'll take some questions. So if we're ready on the first slide, I think it's a video. I'm not sure how well it'll play, but we can give it a shot.
Okay, so I need to go with this one.
All good ideas start as crazy ideas, and then at some point they occur. Then they become, why haven't we been doing that all along? We are right now in that transition for changing the way people think about the moon. The Apollo missions were like Christopher Columbus and the early explorers that came over to the New World. This generation right now is like the Mayflower. It's time to go back. It's time to discover the riches of the New World. We need to go back to stay. We need to go back to push humanity beyond Earth. We need to go back to become a multi-planet species.
Yeah, so just a little bit of an intro about what we're about. So if we just head to the title slide, we are Astrobotic. We're all about making space accessible to the world, and we are starting with the moon. So the first question you might ask on the next slide, why space in the first place? And the way we think about it is it makes life better. There's four main pillars of space, and the first is communications, navigation, Earth observation, and defense. These four are the main drivers of a lot of the $360 billion space industry worldwide. And this is how it's integrated in our life every day, and how a lot of us don't even think about it on an everyday basis, on how much our lives are improved by things in space. And a lot of this is done with commercial activities, especially the first two. which is a really big accomplishment for us to be operating sustainably with a commercial model. So if you hit slide 4, in the past 60 years approximately of space, just to kind of put it all into context, there's been about 6,600 spacecraft, and that number's going up quite a bit these days, in the vicinity of Earth. We've spent about 40 years living and working around Earth with all the various space stations. About 16 nations can independently access Earth's orbit. But if you could take one step further out from Earth and just go to the moon, there's only been about 65 or so spacecraft that have orbited or landed on the surface of the moon. And we've only ever lived there for about 2 weeks. That's the sum of all of the Apollo missions. And only about 6 nations have ever touched the surface or orbited the moon. So we are really just scratched the surface of accessing the moon and figuring out what's there. And then if you go beyond the moon, we've never sent people out beyond the moon, and there's only about 100 or 133 spacecraft that have gone anywhere else. So it's really this slide is all about trying to say we are very focused on ourselves right now, looking back on Earth and supporting life here on Earth, but there is a lot yet to be explored beyond Earth. So if we hit our next slide on slide 5, one of the biggest reasons that we need to keep going to space is that Earth will need more resources, and space has lots of resources, including rare earth metals and platinum groups. And one of the most interesting things in the near term for the moon, and we'll get into this a little bit later, is rocket fuel. So we can take water from the poles of the moon and split it and turn it into rocket fuel, and that's a huge opportunity for reaching the vastness of our own solar system, and maybe one day reaching beyond the solar system. Number 6, slide 6, the other reason to keep going in space is that we have only one place to live. And that's really a big realization that I think the Apollo astronauts showed all of us, is that we are just a tiny blue marble floating in the vastness of space. And there's so much about space and the whole rest of the solar system that we just don't understand yet. And there's ways that we can improve life on Earth and learn to protect our own Earth by understanding and learning how to live in other places in our own solar system. And then slide 7, the other big reason to go to space is that we just need to understand. It's inherent in human nature to have curiosity. And these are, what I love about these pictures, these are real pictures of real places that are out there. And it's just amazing to think that if you're standing in the right spot, and maybe in a spacecraft out there, that this is what you could potentially see. And it's just amazing that these are real places that are really out there. And it just kind of shows us how we have just scratched the very, very surface of what's out there beyond Earth. And ultimately, maybe we can find life out there beyond Earth. If you think about the billions of star systems and planets and everything else out there, I think it's very likely that we'll find life out there. And I think that's ultimately our job to find it and maybe beat it. So on slide 8, this again, I'm not sure if the video is going to work, but it gives a good sense of all the satellites. There's a cool website you can go to where you can click and view all of the satellites that are orbiting the Earth today. And this is a view of that. You can see a lot of them clustered in close and low Earth orbit. There's a few kind of mixed around in the mid-Earth orbits, and then that belt all the way out there is the GSO belt, the geosynchronous orbit. That's where a lot of the satellites hang out to do direct TV and all kinds of things around Earth. But I think what's interesting about this is all of these satellites orbiting Earth, and you take one step out and you look at the moon out there, and the moon's pretty quiet. But that is changing, and that leads us to the next slide about why we should go to the moon. That's a big focus for the talk today. So the big things that we think about, the big things that we're really excited about, first and foremost, is fuel at the poles of the moon, and that is the water. So if we can find water at the poles of the moon, you can split it into oxygen and hydrogen, you can condense it, and that's rocket fuel. That's the same fuel that powered the shuttle. The next is potentially mining. So there's rare earth metals, there's other potentially interesting, valuable minerals up there. Maybe it's mining for use here on Earth. Maybe it's mining for use to create and like 3D print parts on the surface of the moon for replacement parts, or building something there, or maybe refueling and resupplying things that can go beyond the moon. There could be really interesting ways to manufacture things on the surface in microgravity and a vacuum environment. And then a huge question on the moon is all of the exploration and science that has yet to be answered on the moon. I talked a lot about the water already. Another really big discovery on the moon that I don't think gets enough attention is the caves under the surface of the moon. The picture in the top right is actually a picture of an entrance to a cave, and it tells us why it was so hard to find in the first place. And that's because it looks a lot like a crater. With various satellites, LRO in particular found a ton of these cave entrances. And what's really interesting about caves on the moon is if you can get inside of it, it's natural protection from the elements. So it's a little bit like how humans settled in caves here on Earth, natural protection from the elements. On the moon, you need that same protection, and the caves might be a good place to do that. It's meters and meters of rock protect you from radiation that comes from the sun. It's protection from small meteorites that can come in. It's also protection from the thermal extremes on the surface. So it's one temperature underground and much more sustainable and reliable. So ultimately, we think about the moon as the place where we need to go to learn to live off the land of another planetary body. We so far bring almost everything we need into space and to live there. But imagine if we could go to another planetary body, know that we can extract fuel, know that we can print 3D parts from the local terrain, and know that we can pretty much live off of that land. That potentially could dramatically open up our solar system to exploration. And we need to take those first few steps, and we think the nearest term step towards that is the water fuel at the pole of the moon. And we have a very interesting mission that I'll be talking about a little later about that very first step that NASA and us are working on together. So if you go to slide 10, this is just a kind of a glory shot of what could be on the surface of the moon. So ultimately, our first mission, Peregrine, is flying late next year to the surface of the moon and delivering payloads up to the surface. This might be what it looks like. What I like about this picture is we're based in Pittsburgh, and this is a real picture of a lander with real terrain, and obviously the Earth is photoshopped in. But what's really fun is that this is a slag heap, which is the tailings from the steel industry. And we go out there at night with big bright light, and it looks just like the moon. So it's a really, really nice testing ground for us that's local and rooted in the historic nature of Pittsburgh. So on slide 11, this is a little bit of a preview of all the different services and platforms that we build at Astrobotic. We're all about delivering end-to-end services. And in this case, we think about lunar delivery by the kilogram. So we take science missions and exploration and robots and technology demonstration missions, and even various commercial missions up to the surface. And we take it up by the kilogram. So Peregrine, our first lander, can take about 100 kilograms to the surface of the moon. Griffin, which is our most recent mission win, can take about 500 kilograms to the surface of the moon. And then Cube Rover and Polaris are the two rover vehicles that can take payloads across the moon. So the idea is not just get to the moon and stay, but also be able to drive across it, take instruments across, go and explore. And in particular, with larger vehicles, potentially drill for ice and maybe one day be able to extract that into usable amounts of fuel for refueling capability. So if you jump to slide 12, this is a real summary of what we do. We actually think of ourselves a little bit like a delivery service. So we often say DHL to the moon. And that is how we like to think about the interactions with our customers. So the customer delivers a payload to us. We then attach it to our lander. We buy a ride on a launch vehicle to get us up to space, and then the launch vehicle flies us towards the moon. Our lander goes the rest of the way. We drop into lunar orbit. We descend down to the surface for a soft landing, and that's where we deploy payloads. And then the lander becomes the local power station and utility station for supporting those payloads. So if you go to slide 13, this is going to be a progression of pictures, so you might be able to click through them. So what does it mean if we make the moon accessible to the world? So this is just a little snapshot of some of the payloads that we have on our first mission. So the first payload is a NASA payload as part of an $80 million contract we got last year for our first mission. This is part of the NASA CLIPS program, which is a commercial lunar payload services program very innovative, cutting edge program where NASA is buying payload delivery services just like we sell, and really pushing us to a new frontier of exploration on the moon. But this payload in particular is one that's looking at the terrain and trying to figure out what the material properties are of the soil. So it's a precursor towards that towards water exploration. The next payload is the Mexican Space Agency. So the Mexican Space Agency could be the fourth nation to operate payloads on the surface of the moon after China. And that's pretty cool for them. And that's enabled by our delivery service. So they're sending small rovers up to the surface of the moon. SpaceBit is the next one from the United Kingdom. They're actually sending a small, almost CubeSat with legs vehicle up to the surface. Very cool looking. I can't wait to see this one fly. And it's just primarily technology demonstration, but they're building up toward bigger and bigger plans. So if you hit one more, we also have a payload from the other side of the world, from Nepal. So there was actually an astronaut that brought a moon rock to the peak of Everest, and now Nepal is sending a piece of Everest back to the moon. So full circle. We're also working with schools in the local area of Mount Everest, and who are also contributing artwork that will be sent up to the surface. So we are really trying to reach the whole world here, and make the moon accessible. And then the last one here is just a local example in Pittsburgh, where we partnered with a history center there, and they had a vote for Pittsburghers about what Pittsburgh wants to send to the moon. So there was the terrible towel of the Pittsburgh Steelers. There was some local food restaurants. There were songs from Mr. Rogers' Neighborhood. But the one that won was actually a token from a local Kennywood amusement park that's going to be going up. So it's just cool little snapshots of all the things that human stories that can connect to the moon, and then also really push us further with science and exploration. So if you go to the next slide, slide 14, this is a snapshot of the Peregrine Mission 1 manifest. The big idea here is that we have a whole mix of different payloads on here. We've got DHL as a sponsor. We have a few commercial payloads that are sending rovers and even some marketing kinds of things up to the surface. And then we also, of course, have NASA as one of our largest customers on our first mission, sending a suite of payloads up to the surface. But it's just really, really exciting to see that the world is super excited to go back to the moon. And it's more than just the space agencies. It's commercial organizations. There is a market developing here in its early stages that really could be super exciting for the long run for a very diverse market out on the moon's surface. So if you go to 15, this is one of NASA's slides, but just to kind of tell the arc and the story here, NASA has hugely exciting plans for the moon. The first is the big flagship program is the Artemis program, where they plan to land the first woman on the surface of the moon by 2024. And what an amazing thing that would be, to be going back to the moon a little more than 50 years since Apollo first landed there. And that's going to have some precursor missions. The Commercial Lunar Payload Services program is one of the big robotic precursor programs. They're planning on sending about 2 missions, potentially more, to the surface of the moon over time. We're lucky enough to have 2 of those missions so far, and for 2021 and 2023, and then we've got some competitors that have a couple of those missions as well. So really exciting start to our return to the moon and taking it to the next level here. Slide 16 is going to be a video. It's going to have a little bit of a soundtrack. Hopefully we can turn it down and I can talk over it, but maybe we can start that.
Mission 1, 0, and liftoff.
So maybe we can turn the volume down a little bit. So I'll kind of narrate over this one. So this is our mission video. So the way this works is we start on for the first mission, we start on a Vulcan launch vehicle that will fly from Florida. We share the ride to space. This is about a 200-foot tall launch vehicle, 2-stage vehicle with solid rocket motors that just came off. When we're high enough up in the air, the fairing separates, and that means that the atmosphere is thin enough so that it doesn't interfere with any of the payloads on top. When the first stage finishes its burn, it separates. Second stage relights. Now we don't see our lander yet because we're sharing that ride to space. So the primary payload is going to separate from the vehicle. We're going to spin around and we're going to jettison the adapter, and then when we spin back around again, we'll see the lander for the first time on top of that second stage. And then the second stage fires and pushes us out towards space. And then when we're close to Earth still, but have a trajectory towards the moon, that's when the launch vehicle lets go, and that's where our job starts. So this is our lander flying out towards the surface of the moon. We'll do trajectory correction maneuvers along the way to make sure that we're lined up. We soft land down on the surface after a couple orbits, and then once we're on the surface, we become the local utility and the power station for payloads that come with us. You can just see some of those payloads attached to that. And hopefully I was somewhat lined up with the video on there. So if you go to slide 17, this is just a quick snapshot of the video that we just saw about the trajectory. So we start from Florida, go to one phasing loop around Earth to get the right direction and everything lined up. And then we do a burn to get us out towards the moon for capture. And then we do subsequently lower and lower orbits until we circularize and then descend for a soft landing down on the surface. Slide 18, if the video works. Not sure if this one's going to work, but this one just kind of shows that same thing from an STK analysis that shows us flying out towards the surface. And we can probably skip over that one and go straight to slide 19. This is the landing site and surface operations slide. So the destination for our first mission is a place called Lacus Mortis. It's about 44 degrees north, 25 degrees east on the moon, so the upper right-hand quadrant. We picked this location because it's fairly benign from a thermal situation, fairly easy to communicate to back home still. You don't get the effects that you might get to degrade your radio communications that you get at the pole of the moon. So here at this location, this is just a nice, easy place to try to start the landing. The other interesting thing in the region is that there is one of the potential entrance to a cave under the surface. Unfortunately, we won't be landing close enough to it, but potentially on a future mission, we could return to see if there is in fact an entrance there. So if we go to slide 20, this is a little bit about our lander itself. So this is the Peregrine lander. It's about 6 feet tall, about 8 feet in diameter. And the lander here this is our delivery truck. So we have payloads that attach here. They attach to the outside edges of the deck spaces, and those payloads can get carried up to the surface and delivered. We got a solar panel to get power during cruise and also on the surface of the moon. We've got 12 attitude control thrusters spread around the lander for small little maneuvers to line up our 5 main engines underneath. Fuel is 2 fuel tanks, 2 oxidizer, and it's MMH MON 25 pressurized with helium. And that provides a nice, reliable, actually deep space compatible fuel system for the vehicle. When we get down close to the surface of the moon, we use a LiDAR optical head, and that gets us our altitude as we're coming down so that we can make sure that we know where we are on our way down to the surface. So if we go to slide 21, the whole idea with Peregrine is we want to make this a commercial product line that can be modified slightly for payloads, but the idea is to try to modify as little as possible so that we can build many, many, many of these and keep costs low for our customers. So the vehicle is designed to go to multiple locations on the moon. The first mission is to Lacus Mortis, as I mentioned, but we can also do the equator. We can do the poles. We could potentially also deploy payloads into orbit around the moon. So a lot of options there. Slide 22. These are a few videos. If we can just kind of play them all at once, that's fine. So we are building and cutting metal right now. And I'll show a picture of some completed structure here in the bottom. Our partner Airbus is doing drop tests on the legs. We actually got their first engineering unit of the legs in just the other day. Things look great on that. And we've also done some vibration testing on an early test model. We actually just finished completion of a brand new structural test model, and that's going to be tested in the next few weeks. So if we go to the next slide here, we've also done engine hot fires. So this is a video of the engine firing in a vacuum, which is a pretty remarkable thing if you think about it. You're firing gases and lighting them up inside of a vacuum, and the vacuum is designed in a way that it can pull those gases out fast enough to essentially simulate firing in a vacuum. So it's a quite impressive test setup to make this happen. But engines are working great, and development is going very well there. Slide 24. This is our avionics units. This is the computer for the system. There's quite a bit more of this built up at this point, but these are some earlier pictures of our flight computer and power management boards coming together. We are sourcing a lot of the components off the shelf, but we are building up our own boards and a computer system for the Peregrine lander. And if you go to slide 25, you can get a view of our new structural test model. This was just completed last week. We finished the last bits of this, and this is getting ready to go off for structural testing. So we're going to have it on a shake table and shake it in a few different axes, make sure it lines up with our model and fits our analysis profiles to ensure that we can survive launch. So it doesn't have all the mass models on here in these pictures, but they will be loaded up for the test. So if we go to slide 26 here, to give you a sense about where we are, we just finished our structural test model as I just talked about. We are working on all aspects of the mission, from mission control to propulsion, and we've got all of our suppliers out working on all the components. So all the flight parts will start coming in towards the end of this year to early next year. And then we'll be integrating, doing spacecraft testing as a full up unit, and then heading it down to Florida to put on the Vulcan launch vehicle and launching it up for our mission late next year. So that's Peregrine. So if we go to this next slide, this is just a little bit on our second mission. So our first mission goes to the end of 2021. Our second mission is a Moon Ranger mission. And this is a payload development funded by NASA, where this mission is going to be flown on one of our competitors' landers. But we are building the rover along with Carnegie Mellon to build an autonomous vehicle that can drive across the surface of the moon and demonstrate autonomy, which is a key aspect of driving and operating and surviving in the extremes of the lunar terrain. So if we just hit slide 28 here. We've got some test platforms that we're developing that navigation and autonomy systems with. You can see some of this out in the field. We've got a line striping configuration, and you can see the terrain reconstruction on the right there. This is what the robot sees as it's driving along. So it's not too different than what we see with the autonomous cars. That this is actually the same group where a lot of that autonomous car technology came out of. But this is our general approach for having the robot see what's in its surroundings and then be able to navigate and react autonomously to that. Slide 29. You can see some of our good technical progress on the actual mobility system for that vehicle. So we have some prototype wheels and an engineering unit of the mobility system, and you can see it here being tested on a slope testing facility. So far things are going really well with it, and we are excited. And that mission is currently scheduled for sometime in 2022, and that's going on a Maston lander. So next slide 30. This is a new big exciting opportunity for us. So just a few weeks ago, we landed a $200 million opportunity with NASA to deliver the NASA Viper rover to the pole of the moon. What's extremely exciting about this mission is that the Viper rover is going to be outfitted with a drill that will drill into the shadowed parts of the pole of the moon and look for water. And if we can find water at the poles of the moon, as I mentioned before, that is a huge leap forward in our ability to learn to live off the land, potentially our ability to refuel spacecraft on the surface of the moon, potentially our ability to refuel spacecraft in the vicinity of the moon, i.e. orbit around the moon. So this could be one of the first times that we're able to use materials from another planetary body in a useful way for our future missions. So a huge opportunity here with NASA, and it's just so exciting to be a part of this mission. So the way this mission works is we fly in a launch vehicle similar to Peregrine. This is our Griffin vehicle, so this is a much larger lander than the Peregrine lander. This one can take 475 kilograms to the pole of the moon. It deploys the rover with dual ramps, so as you can see in the image, and the rover can drive off whichever way is safest. And then once the lander is away, we'll be able to capture video and pictures of it just testing itself out, making sure everything is working right. And then the rover will drive off on a multi-kilometer traverse over several weeks, going in and out of shadowed craters. So a very exciting mission. So slide 31 here shows a little bit more of the tech specs of this. But just while people are kind of skimming this, I think what's really exciting about this mission is this will be the first time ever that anyone will have sent rovers to the pole of the moon. And for Astrobotic to be a part of a historic mission like this with ginormous science return, and really a huge milestone towards getting off Earth resources to be used is just a real honor to be a part of it. So this mission is planned for 2023. So we're in the design phase for our Griffin lander, and we're working very closely with the Viper, the NASA Viper team in the development of the integration of their rover to our lander. And again, we're just so excited about this mission. So if we move on to slide 33, the missions going to the moon, the first mission, we're going to have a lander that can land within a few kilometers of a target. The second mission, the Griffin mission, is going to be able to land within 100 meters of a target. And that's enabled by a precision landing system that is able to use cameras on board. And we use the cameras to match that up with onboard maps. And we look for the features. We say, oh, there's a crater and there's a crater, and that looks kind of like this part of the map. And then we use that to navigate precisely down to the surface. Once we get close to the surface, that's when our hazard detection and avoidance system turns on. So that's able to scan the terrain, look for rocks, look for slopes, look for craters that weren't imaged previously, so that we can make sure that we can land safely. So if we go to slide 34, this is a demonstration video of that system working. This is a few years back. This is a Maston vertical takeoff and testing vehicle. And we can just kind of play through it. Sounds like it's going. So what this video will show is the vehicle goes up about 250 meters vertically. And then we turn on our scanners and our LiDAR system and cameras. You can see it scanning the terrain as we're traversing over to the landing site. We're looking for rocks and boulders, and in this case, bushes, because of course it's Earth. We build up those maps. We build up a hazard map here. We draw basically red circles around things that are bad and find areas that are green, nice and flat. We command the vehicle to go over to one of those flat spots, does a little divert, goes over to the flat spot and lands. So this was, as far as we know, the first autonomous free flyer, rocket fueled propulsed free flyer for autonomous landing, which is at least on Earth for precision landing. So very exciting for us. But this is the basis of the technology that will enable a precision landing with the Griffin vehicle and our future missions. So slide 35, if we head to that one, this one just shows an idea of modeling the poles of the moon and how we have to think about the challenges at the poles. So I think there's a video here. If we play that, you can see that the left side is actually video from LRO, and LRO takes video in strips of images. But those strips the lighting is changing, and it's very specific to the time of day. So in order to be able to plan any landing at the pole of the moon at a specific time, you need a full map. So we were able to create that map, and that's the visual simulator on the right. So this is computer generated map on the right, comparing it to the actual images on the left. And you can see that we're rotating the sun and getting the shadows to fall as they do. and correlating that. And that's very important because now we can call up any location, any time at the pole of the moon, and we know exactly what the lighting conditions are at that destination. So if we go to slide 36, we can see what that looks like in a landing simulation. So again, we can call up that location, set the light just right, and see what it's like to land at a specific spot at the pole of the moon. And this is very important to inform our terrain relative navigation system, which is looking for those specific features so that we can do a nice safe landing on the surface. So jumping to slide 37, we also have a great deal of effort in the rovers. As I mentioned, with the Moon Ranger contract, we've got all other rovers. We've got large rovers and small rovers. So if we go to slide 38, this is a quick snapshot of our Polaris rover. This one is not yet destined for a mission, but it is a vehicle we are in development of. This one is designed to go to the poles of the moon. It's about a 200-kilogram rover. And it's got vertical solar panels to catch the sun and drive around at the poles. We can house large payloads inside of this, including potentially drills. So a nice platform for the pole. Slide 39. This one in particular, I'm very excited about. This is our Cube Rover product line. This is a small-scale rover designed to be very lightweight and as affordable as possible to make it possible for universities and even commercial organizations to have a rover on the moon and execute various missions, whether it be science or exploration, technology demonstration, maybe even something fun for commercial aspects. So to give a sense, we can build rovers on order between 2 to 10 kilograms and payload masses from 1 to 6 kilograms. So we can have a purpose-built rover for a specific science payload, for example. The rover communicates with Wi-Fi back to the lander, and then the lander relays that signal back home. And if we go to slide 40, you can see the structural test model for that is being built up now, and that's the backbone basically of the small rover. Slide 41 talks a little bit about DHL Moonbox. So this is, we're all about making space accessible to the world, and most of what I've talked about so far is all the various science and payloads that are going on our landers. But those are typically $1.2 million per kilogram. So out of reach of many, many, many organizations. DHL Moonbox is designed to change that. So the idea here is to have a very small package, but the idea is if it fits at ships, that starts in the few $100 range. So that makes it possible for individuals all over the world to send things up to the surface. So we have lots of these orders for contributing to this time capsule that will sit on the lander for all time. And people are sending inscriptions of people's names. They'll send a swatch from a wedding dress. We have folks that are sending family photos. We even have one family sending hair from their family pet that'll go up to the surface. And this all just sits inside of a time capsule on the lander. And it's just a great way to tie our individual stories to the surface of the moon and change the way we look at it in the night sky and start to think about it as a place that humans can go and start to think about how we can take advantage of the moon and use its resources to further our own interests in science and exploration and really push us into the stars. Slide 42. This one is announcing a new headquarters that we're building in Pittsburgh. So we're Astrobotic based in Pittsburgh. We recently acquired a building there that's just a couple blocks from Heinz Field where the Steelers play. And we are renovating that out into our new headquarters, worldwide headquarters. So if you go to slide 43, you can see a shot of the view as you walk in. And yes, that's a giant lander on the roof. We'd like to see if we can get a lander on the roof so that people can see it and know that Pittsburgh is where these lander missions are happening. And that when people watch the Steeler games, maybe they'll show a picture of that and just kind of have some fun with that and show that we're here, we're loud and proud and excited to be delivering payloads to the surface of the moon. Slide 44. This is a new image of what mission control looks like on the inside of the building and hopefully what it will be after a successful mission. So we've got banks and banks of computers here for all of our operators. Right next door to this is where our customers will sit in their own array of computers with big screens in the front. So this is where the action is during the mission. Slide 45. We do plan to have a museum as part of our building. So the idea is to make it possible for the whole region to walk right up to the glass and see the development of our lander being built. So we again want to make space accessible to the world. And we think that also means making it accessible to our region, our neighbors, our neighborhood in particular, to make it truly accessible for everybody to come up and enjoy it and just experience the thrill of space flight, the reason that we all do it, the excitement that we all get. So slide 46 is a video. This is, our vision is to make the moon accessible to the world. We ultimately want to land numerous missions on the surface, numerous landers. And we hope that soon we'll be able to show videos like this that are actually from the surface of the moon. And we're really excited to be doing what we're doing. So I've just got one more video, and we can play that. I'm going to be quiet on this one, and then after that we can open things up for any questions. And I think that's going to be slide 47. It should have some sound.
Ignition sequence start.
I'm sure some people are thinking, we've kind of already done the moon. We went there in the 60s, right? Why spend all this time and money to go back?
Humanity has an inevitable destiny in space, and a moon landing enterprise is absolutely essential to deep space exploration, development, and science that is yet to come.
The moon is our nearest neighbor, and it's a place where we will need to go to learn to live off the land. It's the natural next step. This is the moment in history when people will look back and say that this is the turning point for pushing humanity deep into space.
There is no uninventing, and there is no going back. These transformations are forever.
And we could just go to the last slide, and I'll take any questions. Thanks for having me here today.
Yeah, that's really fantastic. Very, very exciting. So anyone have a question, please type in chat box or, raise your hand to get you unmuted. Okay, Lisa, 1 second. Okay, go ahead, Lisa.
Hi, thank you very much. That's such an impressive presentation, and congratulations on your contracts and everything that you're doing with NASA. I'm a NASA JPL Solar System Ambassador, but also a committee member with Charleston Women in Tech. And
awesome.
We have over, yes. So I congratulate you on especially putting the steel workers and the steel worker industry back to work. That is impressive. And the committee that I am involved with are 2,800 women that are from the DoD, technology, space, science, STEAM, civilian, data scientists. It's incredible, but we're all, going through COVID, which we are completely accessible and worked in remote areas where when COVID occurred, we comfortably settled in.
That's great.
With your things that you are doing, I love the LRO and how you found the cave. That is so amazing. Your partnerships, do you see anything as far as doing things with academia, the universities? I mean, we have one group that with the first autonomous robotics program, NASA autonomous robotics program, they won first place and were supposed to go to Houston, but of course with COVID, they were shut down. But for our 21st century workforce, we're trying to keep them going.
Yeah, absolutely. And we do have partnerships with universities. So we so several partnerships. So the closest to home is a partnership with Carnegie Mellon. And they're leading a fair amount of the rover development, especially of the Moon Ranger rover. And then we also have partnerships with some of our other payload customers. So the Mexican Space Agency actually contracted with a university in Mexico, and the students there are getting involved in the development of that payload. And we have multiple, even high schools that are sending time capsules up to the surface of the moon with our digital moon box. So we are really interested in partnerships. We really do want to make the moon accessible. So I'm happy to have a conversation to see if there's ways to potentially work together.
Yes, excellent. Hopefully at the end, I can get an email to contact with you or have a discussion, because we had our high school students complete. I gave a 3D printing from 2014 from our archives. I did a webcast, and it started a federal, state, and local level process of 3D printing PPE for our healthcare workers and first responders. And that was a great way to get our high schools and universities active in these measures. So thank you very much. Yes, thank you.
Oh, thank you. Appreciate it.
John, I mean, while we're waiting for more questions, can you comment a little bit about your effort with Dynetics for the HLS?
Sure. Yeah. So we have we're a subcontractor for Dynetics, and Dynetics recently won one of the human lander bids to build up a human lander to go to the surface of the moon. So our role on that contract with Dynetics is to lead the business development of delivering payloads on the human lander. So, I mean, effectively, anytime a lander is going to the surface of the moon, we want to be able to maximize the science or the output for humans or anything that we can possibly do. And we see an opportunity there to potentially expand our delivery service capability into the human landers as well, so that we can have science and exploration going on simultaneously with the human exploration aspect of those missions. So we're very, very excited about that. We also will be doing the same kind of payload integration things that we do on our own lander, but very excited about that partnership with Dynetics, and I think they have a fantastic platform, and I think one of the best ones there for delivering humans to the surface of the moon, and we're just really delighted to be a part of that program.
Excellent. And you mentioned you work with Carnegie Mellon University. So is any specific department? I heard there's I don't know if it's still there. It's called the Planetary Robotics Institute. So it's
yes,
kind of...
that's exactly the group that we work with, and which is part of the Field Robotics Center at Carnegie Mellon under Red Whitaker. So we work very closely with Red, and we actually spun out of that university about 13 years ago. And we still maintain close ties. So it is the robotics part of Carnegie Mellon, and they've got several quite a lot going on in the space world.
Oh, I see. Very, very exciting. I see. So let me see. Errol, do you have a question? I saw you have. Do you want to say something? Errol? Let's see. By the way, you mentioned this DHL. You used their logo, so that do you mean that DHL actually is funding this mission, or they are partner with you?
It's actually both. So they're a partner of our mission, and they're also a sponsor of that mission. So we're going to be sending their logos to the surface of the moon. They worked with us on the branding for DHL Moonbox. They're excited because they're a shipping company and we're a shipping company. And now DHL can say that they not only deliver to every country in the world, but also the moon. So it's very exciting for the both of us, and I think it's just a natural partnership for us to be working together.
I see. Okay. So on your website, you mentioned, you said the low cost of the component for people can purchase $100, like $1,000 to put their, as you said, their time capsule, those things. So do you also censor what's inside, or you just took whatever was ordered?
So we do have to be careful about that. We ask every one of the customers to report what's inside, and obviously we will see what's inside because we have to then report that to the FAA for clearance for flight. So we will certainly be reasonable about that. We've had no issue so far. People understand the purpose there and have been really good about it. But we'll certainly be watching for anything that might be inappropriate, but so far we've had no issue with that.
Yeah, okay, I see. I think Lisa has a comment about this. Lisa, do you want to say something?
Oh, yes, hi. One more question, just regards to DHL. The commercialization that you will be doing, and you're a subcontractor for Dynetics. With DHL sponsoring your programs, and also the commercialization with the payloads, do you see Astrobotic using the gateway to help with these payloads, or are you going straight to the moon?
So when Gateway is available, we'll be using Gateway in various different ways. At least we'd like to be able to use it in various different ways. So the early missions, we're all going straight to the moon. But as soon as Gateway is available, our intention is to hopefully work with NASA to use it first as a relay station for communication, because it will be much higher bandwidth than what's typically possible directly from the moon. The next is potentially being able to use it as a relay for the far side missions, so missions that don't have direct line of sight back to Earth. Then the other possibilities is to use the Gateway as a location to return samples from the surface of the moon. It's much easier to make a vehicle that can fly from the surface of the moon up to Gateway than it is to make a vehicle that could fly from the surface of the moon all the way back to Earth and be captured. So that's a very compelling part of Gateway for sample return. And then in deeper time, potentially, which I'm very excited about, is potentially remote operations of rovers via Gateway. The challenging part of operating rovers from here on Earth on the moon is the time delay. There's anywhere between 6 and 30 seconds of time delay for operating a rover. But if you're in orbit around the moon with the rover right beneath you, it's essentially real time. So you can do much more intricate maneuvers or things. So imagine like a very dexterous robotic arm and hand that could go down to the surface and look at a specific rock sample, or turn it over, or poke it, or do whatever you need to do from a geological perspective or science perspective. That could be operated remotely from the Gateway. And that's a really exciting enabling capability that I think we could use that same architecture once tested and developed on the moon to go to Mars, and use that same thing to explore Mars and have robotic vehicles on the surface with humans in orbit. So it's a very, very compelling opportunity with Gateway coming online potentially in the future.
Excellent. That's great. That's so DHL potentially, theoretically, could be used to bring the core samples from Perseverance through the Gateway back to Earth.
Potentially, yeah. I mean,
Okay.
What we would need to do is collect those samples and send it up to Gateway and then send it back to Earth. And DHL does play a significant part of the transportation here on Earth. When you transport spacecraft, there's a lot of special requirements around that, and DHL plays a big role in that.
That's great. Congratulations. That's a great way to have the supply chain command for commercialization in space. That's wonderful. Thank you.
Oh, thank you.
John, this is great. This is really great example for space commercialization. This is really wonderful. Just for fun, I mean, does DHL offer tracking number to deliver people to the moon?
Not yet, but it's definitely in conversation. I don't want to let the cat out of the bag there.
Okay. Yeah, just a quick comment. You mentioned about this telepresence, coming from the gateway. Actually, some of our AIAA folks, like Mr. Dan Adamo, and also Dr. James Logan, they've been proposing, instead of landing on the moon, on the Mars directly, they have been proposing to, because it's more fuel energy efficient, to land actually on Deimos and Phobos and use remote control. Yes. I'll send you information for their. We have their talks in a couple weeks. So they have been proposing that, and they have been trying to promote that doing this, and they can remote control the robot, maybe yours, from Phobos or Deimos.
Well, they should definitely be looking at the moon as a practice ground for that, because there's a lot of activity there, and that could be a great place to prove the tech and make the case even stronger for Phobos and Deimos.
That's wonderful. So do you have any plan for the Mars mission?
Not right now, but it's certainly something that we're keeping track of on the horizon.
Excellent. Okay. I think Victor has a question. Victor, go ahead.
Yeah. Can you hear me okay?
Yes, I can.
Yeah, I was wondering. So the present launch vehicles they're using now, the Delta and Atlas series, are those the ones you guys are going to be using initially, or maybe transition over to SpaceX, something SpaceX might come up with later, or what would you be using for transport your equipment to, say, the gate or to the moon?
Sure. So the first mission we're flying on a United Launch Alliance Vulcan. So that's the upgraded Atlas V vehicle. The second mission with Griffin, we have not yet selected a launch, and we're considering all of our options there. So stay tuned on that one.
All right.
Okay, I think Thomas has a question. Thomas, go ahead.
Yes, I saw Pioneer Astronautics, I think, was just awarded a contract by NASA around regolith and water splitting, some sort of design. Would you be involved in that in any way?
Sorry, you're breaking up just a little bit. I'm not clear on the question.
Okay, Pioneer Astronautics was just awarded a contract to design I think it was a regolith water splitter, trying to, I think, eventually get H2 and O2 out of it. Would Astrobotics be involved in any way in this preliminary design, since somebody's got to get it up there?
So we have not, we don't have an active partnership with them, but we'd be very open to having that conversation with them. The long-term, yes. I mean, that is the business that we're in. We are in the business of delivering things up to the surface. And I would imagine any of those kinds of platforms would need a mobile platform probably to get close to the fuel source, i.e. the water. So that's something that we're watching very closely, and we hope to be co-developing that with the technology for the water extraction. Well, is that maybe the last question?
Hi, it's Lisa again. I have one more question.
Sure.
Are you okay? With regards to the ground base and what you're doing on the moon for space commercialization, will you be part of the process for colonizing the moon on the South Pole?
We would like to be. I think that robotics is going to be a key part of that, and obviously delivery will be a key part of that. So I think we're going to need the robots to go and extract useful amounts of fuel to help build and maintain the base and provide resources back to it and provide transportation and other things for the astronauts. So I think that it's going to really be a human-robot partnership on the surface of the moon, and I think that's going to be a key part. So yes, transportation and robotics are going to be our two big foci there for that development.
Excellent. Thank you so much. That's a wonderful presentation. I'm very excited. Thank you.
Well, thank you. Thank you all for having me here today. Really appreciate it. And I hope you all have a wonderful Saturday.